we have seen that electric field satisfied the equations that its divergence at any point was related to the charge density at that point, and curl of E is always 0. We needed these differential equations because there may be situations where the electric field, although the formula for electric field in free space we had already written was q over 4 pi epsilon 0 1 over r cubed r, or for a charge distribution ER is given as 1 over 4 pi epsilon 0 integration rho r over r minus r prime cubed r minus r prime dv prime, but this is only in free space. This need not be the case, for example, if I take a charge, say, inside a grounded sphere. Then this charge, since this is shielded by a metallic grounded sphere, it need not give a field which is given by the previous formula, and therefore what one needs to do is solve those differential equations with the boundary condition, appropriate boundary condition. We'll talk about it a little more little later. For the time being, let us understand the meaning of curl equation. What does it mean? This will automatically lead us to defining, understanding this will lead us to defining electrostatic potential, which is easier to deal with compared to electric field, because for electric field we have two differential equations. We have equations for its curl as well as its divergence, and we will see that electrostatic potential we will have only one equation because this will be a scalar quantity. So let us see, when I have curl of a quantity is equal to 0, by Stokes' theorem we have over a closed path the line integral of E, which is equal to the area integral of the curl of E, this we did last time, is equal to 0 because this fellow is 0. And therefore, if I take 2 points, 1 and 2, and let me choose one path along this, call this path 1, second path along this, call this path 2, then integral 1 to 2, let's say along path 1, E dot dl is same as integral 1 to 2 along path 2. If the curl of E is 0. This is because from here what I get is 1 to 2 along 1 E dot dl minus 1 to 2 E dot dl along 2, and now I am going to change sign. I will make this plus and change this from 2 to 1, because going from 1 to 2 is same as minus going from 2 to 1, and therefore it becomes 1 to 2 plus 2 to 1, and this becomes integral over the entire path E dot dl, which is 0. So this condition implies this and vice versa. So, curl of 0 we have seen tells me that if I traverse between 2 points 1 and 2, the integral is independent of the path, and therefore, I can write E dot dl between 2 points 1 and 2 is independent of path, and I am going to write this in a particular way. I will write it as minus V2 plus V1. Okay, if curl of E is 0. Let us understand what these V's stand for. You can also write this in a better way, V at R2 plus V at R1. So, I have taken these 2 points 1 and 2, and irrespective of what path I choose to go between these two, E dot dl always turns out to be the same, and that is why I can write it just as a difference between quantities at these 2 points only. Let us write this slightly differently. So, I will write V at R2 minus V at R1 is equal to integral minus E dot dl from 1 to 2. What is minus E? This is force that the person moving a unit charge Q equal to 1 has to apply on the charge to keep it in equilibrium. So, minus E is the force that a person holding the charge has to apply to keep it in equilibrium, and dl is the distance travelled. So, this is dl, this is dl, this is dl, this is dl, and integral means I am adding over all these dl's. This is a force applied by the person, and then the person is moving it. Therefore, this represents the work done. Let me write with a different color. This represents the work done by the person in moving the charge, moving a unit charge. And this V I am going to call the potential. So, potential difference between points 2 and 1 is the work done by an external agency or a person in moving the charge, keeping it in equilibrium, in moving it from 1 to 2. Let us recap it. So, if I am given 2 points and a person moves a charge from point 1 to point 2, this is given as minus E dot dl from 1 to 2. So, the potential difference between point 1 and 2, this I am calling potential at 2, this is potential at 1. So, electrostatic potential difference between 2 points is the work done in moving a unit charge by a person taking it from 1 to 2, and it is independent of the path. Okay? And that is why I can define this potential. All right. So, now what we have understood is that electrostatic potential is equivalent to work done not by the electric field, by an external agency or external, let us write it agency, in moving a unit charge in an electric field from point 1 to 2. Notice that even if I add a constant to both V's, the difference remains the same. and therefore potential is defined only up to a constant, because after all it's the work done or the potential difference which is the physical quantity. So adding a constant to potential does not make a difference, and therefore electrostatic potential is defined up to a constant. That means I can add or subtract any constant in it and nothing, no physics changes. What we have seen is that we have related potential difference to the electric field work done. How about the inverse relationship? How do I express E in terms of the potential? You can already see that since delta V is the integral, it has to be some sort of a derivative, and this introduces the idea of gradient. So for that, let us take 2 points nearby, point 1, which is at x, y, and z, and point 2, which is at x plus delta x, y plus delta y, and z plus delta z. Then minus v at 2 plus v at 1 is going to be minus v at x plus delta x, y plus delta y, z plus delta z, plus v1. And this, by definition of partial derivatives, is equal to minus partial v with respect to partial x, delta x minus partial v over partial y, delta y minus partial derivative of v with respect to z, delta z. Okay, so between points 1 and 2, x, y, z, x plus delta x, y plus delta y, z plus delta z, we have seen that v at 2 plus v at 1 is minus partial v partial x, delta x minus partial v partial y, delta y minus partial v partial z, delta z, and this is equal to E, let us say at x, y, z, dot dl, which is going to be delta x in x direction plus delta y in y direction plus delta z in z direction, which is equal to Ex delta x plus Ey delta y plus Ez delta z. I can take delta x equal to 0, delta y equal to 0, delta z equal to 0, or any other combination, and since so they are arbitrary, and this immediately therefore implies that Ex is nothing but minus partial derivative of v with respect to x, Ey is nothing but partial derivative of v with respect to y, and Ez, the z component of electric field, is minus partial derivative of v with respect to z. And delta v, which is E dot delta L, or E dot delta x x plus delta y y plus delta z. Z is nothing but equal to minus partial v over partial x, delta x minus partial v over partial y, delta y minus partial v over partial z, delta z. I should write a minus sign here because this is minus v2 plus v1. I am going to write this as symbolically as minus gradient of v dot delta L, where delta L is equal to delta x in x direction plus delta y in y direction plus delta z in z direction. And gradient, I am going to write this as x partial x plus y partial y plus z partial z. And this gives me that E electric field is nothing but minus gradient of V. This is the inverse relationship of what we learned earlier. In the next lecture, we are going to learn a few things about the gradient operator and how V and E are related geometrically.